Hello again everyone, welcome back to ptet.chemistry channel. This is a continuation of this topical MCQ on topic 1, which is just to do with mole calculations and stoichiometry. So what's been going on here is that in the old paper they will say use data booklet, which is relevant to this question. In the modern type of question, they just don't tell you anymore. You just gotta think to know that it involves mole calculation, and you will need the periodic table to do your calculations. Anyway, so you have a 0.2 gram of that oxide. We don't know the formula. The formula is Nx or Y, but we know that it's a gas. We know that it occupies 120 cm cube at room temperature and pressure. So we're assuming that it has a molar volume of 24 dm cube per mole. So the molar volume is 24 dm cube per mole, but that is in cm cube. So we also know that 24 dm cube is the same as 24,000 cm cube per mole. So what happened is there is the mole of the gas. It's going to be the same as the mole of the solid, which is 0.2 gram. You just don't know the MR. The MR is going to be 14.0 times X plus 16.0 times Y, because you have X number of nitrogen atom and Y number of oxygen atom. So we know the mole of the solid is the same as the mole of the gas. So what we do is we just set out an algebraic expression. The mole of the gas and X or Y is the same as the mole of the, well, I said solid, but not necessarily it's a solid, but because we're given the mass, so I'm just thinking of it behaving like a solid. Alright, but of course gas have mass as well. It's just that when we use mass over MR, typically we think of it as being solid, but of course the gas has mass as well. So you can say the mole of the gas based on mass, the mole of the gas based on volume. So maybe I can just say the mole of gas based on mass. Okay, that is more accurate, whereas this one is based on volume of the gas. Alright, so mass over MR, so mass over 14x plus 16y is equal to 120 cm cube. I use cm cube here, so I need to use the 24,000 cm cube per mole in order to cancel out and give me mole. Gram over MR, that will give me mole. Alright, the problem with it is that I have got two unknown. So I've got both of these, I bring it up, and then I will get 0.23 times 24,000 over 120. So 14x plus 16y. I can do the calculations on the left, and they give me 46, and that is my algebraic expression. I still don't know what is x and y, and I cannot evaluate it because I got one equation and I've got two unknowns. It's a simultaneous equation kind of problem, is it? But fortunately for us, we are given x and y. So I just need to sub in x equal to 1. So that's 14 times 1 plus 16 times 1 for the first one. That gave me 30. So 14x plus 16y is equal to 46. That is based on the information that they've given us. The first one will give me 30, so that is incorrect. The second one, put in x equal to 1, so 14 plus 16 times 2. That gave me 46, and that is what we want. Alright, you can try the next one because it looks very similar, right? 1 and 2 and 2 and 1. So if you try 14 times 2 plus 16 times 1, you get 44, which is again incorrect because there's only one correct option. Alright. In this next question, so this is a little bit about electrolysis. We're going to coat it with silver. So this sports medal has a total surface area. So you think about the sports medal, usually they are circular like this. Okay, surface area, not the volume, surface area. The mass increased by 0.26 because that is where you add in the silver. So they want how many atoms of silver per surface area per cm cube, sorry, per cm square of the surface area. So we need to find the mole of the silver first, which is 0.216 divided by the atomic mass, 107.9 from the data booklet, the periodic table. I guess I can express it as a full answer, but I choose not to. I'll just use it in the following part. So we know that 1 mole of silver would have Avogadro number of atoms, because 1 mole of something has Avogadro number of atoms. This one you can get from your data booklet in front. There's a list of data there. So 0.216 over 107.9 mole of silver, I will get 0.216 over 107.9 times L number of silver atoms. Okay, but what do the question want? They want how many atoms per cm square. So it's going to be the answer in 2. The answer in 2 divided by 150 cm square. So it's all of these divided by 150 cm cube. So 0.216 divided by 107.9 times 6.02 times 10 to the 23. That will give me the number of silver atoms divided by 150 cm square. I get 8.034 times 10 to the 18. This is atoms, silver atoms per cm square. The closest to 2 significant figure is going to be that, to 2 significant figure. So I guess in a theory paper, I can do this. I guess because this is 2 sig fig, this is 3 sig fig, whether you leave your final answer to 2 or 3 sig fig would have been alright based on the data given. This next question is saying that the amount of calcium ions in a sample of natural water, you use an ion exchange column as shown there. You have a 50 cm³ sample of water, you have calcium sulfate, and then each calcium ion exchange for 2 hydrogen ions. So there's one important information there. When you exchange it with 2 hydrogen ions, then the resulting acidic solution require 25 cm³ of potassium hydroxide. So if we think about it, the calcium 2 plus is to H plus. This is reaction 1. It's the exchange 1 Ca2 plus replaced by 2 H plus. That's the first information there. 1 Ca2 plus replaced by 2 H plus. Your second reaction is between the acid and the base. So if you have the acid and the base, you have H plus OH minus. I guess I can use KOH if you want to. I don't really care about the anion at this point, but that will give me H2O plus K plus. That equation is balanced. It's a neutralization reaction. Essentially, we're just looking at this being base. I could have just used OH minus and then I wouldn't have the K plus being spectator ions. That would have been alright as well. But my point here is this equation is balanced in the sense that it's 1:1. So if I have KOH there, 1 mole of H plus is to 1 mole of KOH. In these kind of calculations, you could do it in 2 steps, alright? But I'm going to do it in 1 step, and the way to think about it is if you have this thing here, you see this is 2 and this is 1, so you can't bring them up together because they are not the same. So what you do is you take a LCM, which is lowest common multiple, your primary school mathematics. The LCM is 2, so this is already 2. To get to 2, you just multiply the whole thing by 1. That means no change. This is 1. I need to get it to LCM 2, so I need to multiply it by 2 throughout. When I multiply by 2 throughout, what will happen is I will get 2:2, which is equal to 1:1. What I've done is I've just multiplied by 2 throughout, and now you can see that this is 2 and 2. Because they are now the same, I can bring them down. That is the whole point of doing the lowest common multiple primary school mathematics. Alright, 1 and then 2. What am I interested in? I'm interested in this and this because they want the calcium sulfate. In fact, I should have another one, which is I guess I could potentially show you another one. Calcium sulfate is to the calcium 2 plus. 1 calcium sulfate gives you 1 calcium 2 plus. So if I have another 1 calcium sulfate here, if I have calcium sulfate here, this will be 1:1:1. I can also just bring that down to that. So essentially, we're just not interested in the Ca2+, we're interested in the CaSO4, which is what they want. They want this, and they want we are given the KOH information, all right? So we have already established the mole ratio, just like that. So the mole of the CaSO4 is to the mole of the KOH. You will know I like to use fraction from all my other tutorial videos on ptet.chemistry because I never go wrong with it, all right? So I've set it up such that calcium sulfate is on top. It doesn't matter which way around you have it, as long as you follow through by the correct mole ratio from the balance equation, and then follow it through on the right hand side with the actual number based on whatever you have on top. Here is calcium sulfate. So it is the concentration of the calcium sulfate. When I put something in a square bracket like this, it refers to the concentration of calcium sulfate multiplied by the volume. So the calcium sulfate was dissolved in 50 cm cubed just now. So it's 50 cm cubed times 10 to the minus 3. That will give me dm cubed times mole per dm cubed. That will give me the mole of the calcium sulfate. The mole of the KOH is given here. That is 25 times 10 to the minus 3. And then multiply by the concentration. So therefore, the concentration of CaSO4 is a half times 25 times 10 to the minus 3 times 1.0 times 10 to the minus 2 divided by 50 times 10 to the minus 3. Pop that into a calculator. And I've got 2.5 times 10 to the power minus 3 mole per dm cubed, which is option A. Alright, at first glance it seems confusing because there are so many information. People will start writing equations, okay, but then essentially you could be thinking about LCM, that is to bring these two together rather than working in one step and then another step and then getting to that. I can do it all in one step. This becomes very important, especially in a paper 3 practical chemistry setting, as well as in more complicated mole calculations kind of problems. In this next question is about balancing equation. So actually this is a redox equation. So under the redox topic, redox changes, which is topic 6, you will do something called using changes in oxidation number to balance redox equation. Okay, so there is a easy way, but there's also a different way, which, you know, it's not easier, it's not better, it's just a different way. It's just to balance it from scratch. If I use oxidation number, which you might not have done in O level, this molecule has no charge, so the overall oxidation number is 0. The nitrogen is what you want to find. The hydrogen is bonded to nitrogen, so the hydrogen is +1. Oxidation number then is nitrogen -3. In NO, you have nitrogen +1 times -2 because the oxidation number of oxygen in a compound tends to be -2 unless it is in peroxide when it's -1, right? Overall molecule has no charge, so that one just give you nitrogen +2. The oxygen is 0, but the oxygen here is -2, the oxygen here is -2. Okay, so thinking about the changes in oxidation number, so 0 to -2 is a decrease of 2, from 0 to -2. From -3 to +2 is an increase of 5. So what we can be thinking about is lowest common multiple, LCM, our old friend, primary school mathematics. Yeah? So you want to balance out the charges 5 and 2. So you need to think about the LCM, which is 2, 1, 5, 5, 1, 1. So the LCM is 10. So I need to multiply this thing by 5. I need to multiply this thing by 2. So I can be thinking about okay, this is a bit tricky now. Because they don't have a 2 there. So what am I supposed to do now? I might have to balance this from scratch actually. I think that's probably easier. If you balance it from scratch, what can you say? If you balance it from scratch, the nitrogen there must equal to the nitrogen there. So W must equal to Y. because the number of nitrogen must balance, right? W must equal to Y, so all of them is like that. What else can I say? The hydrogen. So the hydrogen from there goes all the way to the hydrogen there. So I'm gonna start from balancing from scratch. I don't think I'm capable enough to balance using changes in oxidation number here. Okay, I will do it when we come to redox. All right, let's just balance from scratch. Okay, so starting from the algebra expression, W number of nitrogen equal to Y number of nitrogen. There is 3W of the hydrogen. So this is for the nitrogen. This is for the hydrogen. So 3W of hydrogen is equal to 2Z. So let's just check it. 3 times W is 12. 2 times 6 is 12. So that one is fine. 3 times 4 is 12. 5 times 2 is 10. So I can cross out B. 5 times 3 is 15. 4 times 2 is 8. I can cross out C. 6 times 3 is 18. 4 times 2 is 8. I can cross out D. There's only one answer, which is that. Okay, and you can check the number of oxygen if you want to, but by getting to this and by putting in W and Z, I could get B, C, and D being wrong. Okay, as I just outlined previously, and I think that's probably faster than me doing the changes in oxidation number. But I promise you, once we get to redox changes, we'll do some balancing equation using changes in oxidation number. This is the last question of this 5-question series. So what we have here is we have samples of the 10 cm cube of each of the first 4 members of alkane, n equal to 1 carbon to n equal to 4 carbon. You separately mix it with 70 cm cube of oxygen. You burn them, basically it's called combustion. And then you work out the total volume of residual gas. So this includes CO2 product plus any unreacted oxygen, which is O2. Okay, so let's start by thinking about what actually happens. So if you have CXHY, I hope you know this general equation for combustion of hydrocarbon. You have XCO2 plus Y over 2 H2O. Okay, of course you can balance your equation from scratch. If I have CH4 plus O2, CO2 plus H2O, 4 hydrogen, you give it 2 there. Oxygen is 2, so I need 2 there. So if I have 10 cm cube of the alkane, 70 cm cube of the oxygen. If I have 10 cm cube of the alkane, 70 cm cube of that, how much do I react? Well, I will react all 10 cm cube, but I will only react 20 cm cube because 1 mole reacts with 2 mole, because these are all gases, so their volume ratio is related to the mole ratio, because the mole of a gas is equal to volume of a gas divided by molar volume of a gas. Since the molar volume of a gas is constant for all gases under the same condition, so the mole ratio of the gas is the same as volume ratio of the gas. I'm talking about reacted. I will react 1 mole is to 2 mole. I will react 10 cm cube is to 20 cm cube. So I would produce 10 cm cube there, because 1 cm cube give you 1 mole, give you 1 mole. 10 cm cube give you 10 cm cube. All right. So this is one of the product, but you have leftover. You put in 70 cm cube, you only reacted 20 cm cube, so you have 50 cm cube unreacted oxygen. So residual is equal to 50 plus 10, which is 60 cm cube. So we're looking for 60 cm cube for CH4. 60 cm cube for CH4. So that is CH4. That is not 60 cm cube. That is CH4. That is not 60 cm cube. That is CH4, and that is 50 cm cube. So CH4 there is 50 cm cube. That is CH4, that is 60 cm cube. So that is what we want. And in fact, by elimination, by just working out the first one, you could get the order already. Okay, and obviously as the number of carbon increases, you will get more CO2, you will consume more oxygen, so you have lesser and lesser oxygen that is unreacted. Okay, so I hope that makes sense there. For practice, you can set up an equation for C4H10. Think about this thing, think about the reacting ratio, work out how much is reacted, how much is produced, and how much oxygen is left over. Add them up for your residual gas, because V is residual gas, is any unreacted oxygen, plus the carbon dioxide product. Work it out for C4H10. You should be able to get this answer as well. Alright, this is it for this 5-question series. I hope that was helpful. Calculations are always quite scary for students, but it needs not be. I mean, hopefully with my more calculation strategy will make it better. And if you found them useful, do subscribe to the channel. Share the channel widely with friends, classmates, your social network, which is probably far more extensive than mine. And even share them with the teachers as well. They might find it useful. And thank you for watching. I'll see you in the next video.